My name is Peter Matrano, and I will be discussing our paper titled Data Augmentation for Manipulation. In this work, we propose a data augmentation algorithm to increase data efficiency for learning robotic manipulation. Data augmentation has been used to great effect in computer vision. For instance, in an image classification task, we can sometimes apply random rotations or crops to the input without changing the class label. Prior work has shown that models trained on these augmented examples generalize better than those trained without augmentation. However, these methods are specific to both data type and task. Although there are well-established augmentations for image and text, the same cannot be said for robotics. We aim to augment trajectories of geometric state and action data. This includes data like object poses, joint configurations, voxel grids, and point clouds. Furthermore, we focus on short trajectories where some objects in the scene and/or the robot are moving. Additionally, we demonstrate the proposed method on both classification and regression problems. I will now describe our proposed augmentation method, then present our experimental results. The correctness and efficacy of our method is subject to the following assumptions, which are discussed further in the paper. At a high level, our method produces augmentations by applying a rigid body transformation to objects in the scene. Specifically, we divide objects in the scene into three categories: the robot, the moved objects, and the environment. We frame augmentation as the following optimization problem, where we consider three terms: validity, relevance, and diversity. We define an augmented example as valid if it obeys the laws of physics. Augmentations are relevant if they are similar to data that would be seen when performing the target task. Diversity is maximized when the transformations applied to a given example are uniformly distributed. Given this abstract problem, we then define a tractable approximation specifically for robotic manipulation. This approximation contains 6 objective terms, weighted by parameters beta 1 through 4. The first term expresses diversity as the distance to a uniformly randomly sampled target transformation. The next 4 terms define validity and relevance for the moved object state. These terms encourage the object to remain within the workspace bounding box, penalize invalid transformation parameters, and preserve contacts and near contacts with the environment. The final term defines validity for the robot state, which preserves contacts the robot makes with the scene. We solve the optimization problem by splitting it into 2 parts. In part 1, we optimize the validity, relevance, and diversity for the moved object state. In part 2, we optimize the validity of the robot state. First, we evaluated augmentation on a simulated bimanual rope manipulation task, shown here. The robot is holding the ends of the rope and is tasked with placing the middle of the rope within the goal regions under the hooks shown in purple. The planner uses an imperfect model of the rope dynamics, and in order to find accurate plans, it uses a learned classifier which predicts when the dynamics model is accurate. We apply data augmentation to the training data for learning this classifier. We compare against a baseline without any augmentation. Initially, both methods fail to reach the goal, but the method using our augmentation succeeds earlier and more often. If we analyze the success rates averaged over the final 10 iterations, we find that without augmentation, the success rate is 48%, but with augmentation, the success rate is 70%. Finally, we also evaluated our method on bimanual rope manipulation in the real world. The scene here is a mock-up of a car engine bay. The robot must move the rope and place it under the engine without snagging it to set up for lifting the engine. We ran 30 iterations of learning, then froze the models for evaluation. Without augmentation, it succeeded in 7 out of 26 trials, and with augmentation, the robot successfully placed the rope under the engine in 13 out of 26 trials. In summary, we propose a novel method for data augmentation for robotic manipulation. We frame augmentation as an optimization problem and show in 3 experiments that training on augmentations improves performance on downstream tasks in the low data regime. Thank you.